So the recording, it's not messed up like for Parker it's messed up, but it's messed up. All right, so I want to kind of review and back up before we go any farther. And part of that was first to answer a couple of questions about the lab. Lab one was supposed to be due earlier. Go ahead and hold on to that if you missed measurements or if you need to tweak some of that. You got time tomorrow to do that, and then there's a fair amount of questions in the lab instructions. Like those are things that you should answer as part of what you're doing. So don't worry about the labs for right now. Lab 1 and Lab 2, if you want to have over this weekend, have enough time to do the fact that tomorrow, I think, so not everybody got to where they were working with the LEDs. So tomorrow the lab will take care of this and we'll talk more about like specifically what you should be turning in. It's for the most part questions that are inside the lab instructions and a part at the end on troubleshooting. Everybody did troubleshooting. Nothing worked perfectly the right way, even if it was like part of our troubleshooting was realizing how the circuit board was laid out. That's legitimate troubleshooting, like knowing that it's two vertical bars, rows, no connection across the middle, and then some more. This thing is pretty simple in one way. Using it, it's not always straightforward at all. So that's part of your troubleshooting. We didn't know how to use this thing. Now we do. So were there any lab questions before we back to lecture stuff?
I've been spending time writing down some stuff.
Yeah, write stuff down. Good lesson. The more you write down, the less you have to remember. And I learned that the hard way multiple times, like double hard way. I knew this, I should have been writing it down. Write down everything. The more you write down, the less stuff you have to remember. And that's usually always a good thing. Keith, we were just talking about lab stuff. Labs, the things to hand in for Lab 1 and Lab 2. I'm going to push those to be due next week and talk more about those finer details in the lab tomorrow. We're basically wrapping up Lab 2 tomorrow. Okay, so back to lecture stuff. This first homework assignment is on schedule for being due tomorrow. I'm willing to take that Monday if you want a little bit extra time. So what I wanted to do was review the nodal voltage method real quick. Then we'll move on to the Thevenin theorem. Quick step back to the methods, and then some of the theorems. So the whole idea behind the nodal voltage method is we're using our Kirchhoff's current law, ECL, as the foundation for building an equation that we can put in voltages and then solve for voltage. So nodal voltage method. That's pretty much starting with the Kirchhoff's current law. So this is the example that we did, and so the first thing is really to start with Kirchhoff's current law. And remember on this one, that I1 was the current that goes to the 4 ohm resistor. So I1 goes through I1 is that way. I3 was this way. And I2 was straight down. I left out the battery so you can see the main part of what's going on. And our PCL for this equation, I1 and I3 go into that node, I2 comes out. So we had I1 plus I3. So we use KCL as the backbone for this method. The next step is to get rid of all of these currents and write them in terms of voltages. And that's just Ohm's law. So how can I rewrite current I1? I know it's going through resistor R1. So V1 over R1 is I1. V3 over R3 is I3. Then V2 over R2 for I2. So nothing hard, too hard yet. We just PCL, and then let's just work with voltages because this is the nodal voltage method. Once you are at the second equation, that's where we are finding voltages around the circuit. We're at the second bullet point. Okay, so here's where the magic part happens, and this is probably the tricky step. This is tricky for me. Is going from this equation with B1 over R1 into actual numbers that you can get an answer with. And what you have to remember is conceptually, what do I mean about B1? That's the voltage that's dropped by resistor R1. So that is the voltage over that resistor. And you gotta go down, back down super low to what's the definition of voltage? Really, we're talking about a potential difference. So the voltage across this resistor R1 is the resistor, the voltage at the left minus the voltage at the right, VA minus VB. These VAs and VBs, those are actual numbers that you can actually start to put things in. Same thing for three. It's VC minus VB over R3.
Hey, Dr. Higgs.
Yes.
Is that just knowing that the potential difference flows from the higher to the lower?
Yeah.
Right. Okay.
Yeah, that's exactly right. That's why it's VC minus VB, not VB minus VC. Everything is like
Right, because it's always
or VB.
yeah, just looking at the current directions.
Same
It's always like the VH minus VL.
Yeah.
Like the high minus low.
Yeah. So if you do the same reasoning to V2, the high voltage is VB. So that would be VB minus VE over R2. And I know at this point it looks way worse because there's three additional variables in there. But here's where you have a little bit of freedom to make things easier. And once you do that, you can just start reading stuff off the circuit back there. All of these voltages that we're talking about are relative to some point. So that's why V1 is VA minus VB. That was the voltage relative to V. At some point, we can choose one of these voltages to be our ultimate reference or our ground reference. So what we can do is choose VB equal to 0. Because we're essentially measuring all of our voltages, VA, B, and C relative to VD, all your reference points here. That takes out one variable. And all the other voltages it's fine from the picture except for VB. So VA, what's that? That voltage is 28 volts. So this point here is connected to the positive side of the 28 volt battery. VA is 28 volts. Same deal for VC. It's at 7 volts. Once you put in 28 and 7 for VA and VC, you got one equation and one unknown. So this is solvable for VB. It wasn't too hard. Once you have VB, you just start working your way back out of the nesting. So, a couple of quick wrap-up comments. nodal voltage method. These are all the nodal voltages. That's the name, that's why it's called that method. Starts off with Kirchhoff's current law, and from there you want to think about replacing each current with Ohm's law, and once you've got your voltages, it should be close to getting to a solvable situation. Any questions on the nodal voltage method? The homework one is a little bit more complicated than this. There's like a third branch to it. Same way. You're free to choose one of those voltages to be 0. And from, do that wisely. Makes sense here because VD is tied to the negatives of both batteries. Kind of what you're looking for the place to put the 0. So back to theorems. We did the Millman's theorem. And the superposition theorem. Those two that we talked about so far, just keep in mind that those only work for linear circuits, particularly superposition. You can superimpose those circuits and use things like Ohm's law, that's a linear equation. What you can't do are power equations. Power is current and voltage. That's not linear. Why? Both I and B can change. R is constant. I and B are both quantities that can change. So the other way to think of this is it's also I squared R. So I get rid of the V here by subbing in IR. So power goes like current squared, so that's why I can't do superposition. Or Millman's theorem. Or it's power is V squared over R. Both of these are nonlinear, they just don't add up. Anyway, what Thevenin's theorem says is if you have any linear circuit, you have multiple voltages and resistances, you can replace that with the equivalent circuit that is just a single voltage in series, single resistance. So this whole mess, a whole bunch of different resistors and batteries. You can replace that with a single voltage source and a single resistor in series with that voltage source. So pretty much what we're going to do is So Thevenin's theorem says that I'm just going to treat this like a black box. Once you know what happens at the output terminal, you don't care what goes on the inside. However messy the guts of that thing are, if it's a linear circuit, you can make that messiness look like something that's way easier. One of the differences between Thevenin's theorem and its counterpart, which is called Norton's theorem, is that now we're talking about a load resistance. We didn't talk about that with any of the other stuff. We just had a complete circuit, and we found the current in every single part of this. These theorems, Thevenin's and Norton's theorem, apply to two-terminal circuits. Where you've got a bunch of batteries and resistances in there. It's got two output terminals, and across those two output terminals, that's where you're going to connect your load resistor, and you want to know what happens when you put your load resistor to your circuit. So your circuit is that you're building, you like the program, interacting with the outside world is like connecting the load resistor to it. So none of the circuits that we analyzed previously had a load resistor in it. It was 3 resistors and 2 batteries. We can apply Thevenin's theorem to those types of circuits. We just have to pick one of the resistors in a circuit to be the load resistor. The benefit to doing it this way is that we have this kind of simple black box description of what our circuit does, completely independent of the load resistor. So I can ignore my load resistor and just figure out what the circuit does. And now I can apply any load resistor and pretty easily figure out how much current goes through it. Contrast that with so this is a circuit we've been analyzing for a while. What happens if I change R2 to some other resistance value? I'm going to go back through my whole analysis. We do this for the most part. Remember, the way that we solve these networks were to kind of get to where we knew at least one piece of information, one current, or one voltage. We worked our way backwards from that. If you change one of these pieces inside, like R2, everything else changes. What we're trying to do with Thevenin's theorem is kind of figure out what this circuit does in general without R2 here. And then I can put in any value of R2 I want, and the analysis is super simple. Well, I can solve this equation and analyze several times before. Thevenin's theorem. I just make it more general, like I'm gonna call one of my resistors the load resistor. And I can solve a more general version of this. And then if I want to I could go back in and put in whatever I wanted for R2. So for Thevenin's theorem, two things that you're looking for are the equivalent voltage and equivalent resistor that make up the simple circuit. That's the whole goal of the Thevenin's theorem, to figure out VEQ and R. Sometimes you'll see this equivalent voltage here called the Thevenin voltage, so VTH. Same thing. We also need to find its equivalent resistance, which is sometimes called the Thevenin resistance. So I'm going to give you an algorithm for how to find VEQ and REQ. If you stick to that algorithm, this theorem works out. Even when it gets confusing, you just stick with steps I'm about to tell you. That should let you work through all these problems. Thevenin voltage. It's that voltage at your output terminals when the load current is zero. So here's my circuit. Here's the output terminals. That's where my load resistance is. And internally, there's a series resistance, RQ, and voltage, EQ. So I find the Thevenin voltage by setting the load current to be zero. How do I get no current to go through the load resistor? It has to be an open circuit. So that's why the Thevenin voltage, VEQ, is called the open circuit voltage. What's REQ? The Thevenin resistance. That is the resistance that you would measure at the output terminals. If you replace every single battery by a zero resistance one. So I really didn't answer how you find REQ and VEQ. I just told you what they are. The the way that we're gonna find them is by these definitions. So there's still, the evidence theorem is really powerful. It takes some work to get to where you can choose that power. So let's figure this out through an example. And I want to use my voltage divider as the circuit to analyze. Because we already know how this circuit works. We know what the voltage we should see at R1 and R2 is. So there's our circuit, regular old voltage divider. Between these two output terminals in parallel with R2, that's where the load resistor would go. So I said find V Thevenin or VQ. What you have to do is make the load current zero. For the load current to be zero, that means we essentially pulling out that resistor does that. So it's the open circuit voltage. So VEQ is the voltage between those two points. That's what V Thevenin or VEQ is. The way that you find the Thevenin voltage, here's where a little bit this how this way. So part of the Thevenin theorem and Norton theorem involves some of the circuits that you've already done. That's why, and that's also why we're going to do the voltage divider. So we're going to make this circuit here so we're transforming this one battery, two resistor circuit to a one battery, one resistor. So my VEQ or my Thevenin voltage is the voltage across R2. Figure that out however you can. We've already done that when we analyzed the voltage divider circuit. So remember the way the voltage divider worked. Voltage across R2 is R2 over R1 plus R2 times V. Voltage over R1 is R1 over R1. So it's not too hard to get our Thevenin voltage. Next step is to figure out the Thevenin resistance. So by definition, that's a resistance between the output terminals when you replace all the batteries by a zero resistance wire. So get rid of the battery. That is, replace that with a zero resistance wire. B, R Thevenin. Which is the same thing as REQ. R Thevenin is just the resistance you would measure between those two outputs. What is that? There's R2. One, two. They're in parallel. It's a little bit harder to see in this picture for their vertically when they're right above each other, but this top part of R1 is actually connected to the bottom side of R2. That's parallel. So this Thevenin resistance, or this equivalent resistance, is R1 times R2 over R1 plus R2. It's just a quick parallel, two resistors in parallel. So that's our Thevenin resistance. And at this point, we've, for the most part, solved the problem. This voltage divider that we've been messing with, we've replaced that with R Thevenin E Thevenin and the place to put our load resistor right here. Right, so we probably want to know something about the current that's going through our load resistor. The whole point of this process is to figure out what happens when we hook up this load resistor. So we got to know how much current can be going. So this is pretty easy. I've got two resistors in series. So the current that's going through the load resistor the Thevenin voltage, that's what's powering this equivalent circuit, divided by the total resistance, which is just our Thevenin plus our load. I'm going to put back in this mess and that mess, this equation, and I'm going to spare you a whole bunch of algebra. As part L on so this equation ends up being the total current through this load resistor. This equation here holds for anytime you're doing the Thevenin's theorem, you always do this because you always have the Thevenin resistance in series with your load resistance. So this you will always do as part of the Thevenin theorem. How I wrote it down here, I use things that were particular to the actual circuit. So this form that I wrote down as the circuit that you're trying to analyze. This one holds for any Thevenin theorem. And what's useful is you've got an equation now where your current IL, your R1, R2, and B are fixed, so you can see how that depends on the load resistance. If you make the load resistor really, really big, what happens? It went over a really big number you're going to have with a small amount of load current. What questions do you have on the Thevenin? The next step, and this is what we'll start on Friday, is we'll work through an example. Same circuit we've analyzed before, since we know what the answer is going to be. We'll apply the Thevenin theorem to And we'll also, final theorem stop is Norton's theorem. Norton's theorem, it's kind of the reverse of Thevenin's theorem. So this says you can replace any linear circuit by a resistor and a voltage source in series. Norton's theorem says you can replace any linear circuit and replace any linear circuit with a current source in parallel with a resistor. Thevenin is voltage in series with the resistor. Norton is current source. So I Norton in parallel with this resistor R Norton. So we'll end up doing kind of the same thing for the circuit. And you have your choice. You do Thevenin or Norton, they both are equivalent circuits. So one of the cool things is that that Thevenin resistance and Norton resistance are the same thing. So how we found Thevenin resistance, same thing to find Norton. And hopefully this will make more sense Friday from the example. Questions? So quick recap, lab tomorrow, we're wrapping up the first two labs from the semester. Don't worry about turning anything into those until next week. Same for homework one, you can hold on to that until next Monday. All right, anything else? Questions? All right, I will see you guys tomorrow.